Welcome to this scientific lecture on one of the most exciting frontiers in modern chemistry, using nanochemistry to convert carbon dioxide into useful products. This technology could revolutionize how we address climate change while creating valuable materials. Let's begin by understanding the challenge. Carbon dioxide is a greenhouse gas that contributes significantly to climate change. Currently, atmospheric CO2 levels exceed 420 parts per million, the highest in human history. But what if we could transform this liability into an asset? What if carbon dioxide could become a raw material for producing plastics, fuels, and other valuable chemicals? This is where nanochemistry comes in. Before we dive into applications, let's clarify what nanochemistry actually is. Nanochemistry involves designing and manipulating materials at the nanoscale, typically between 1 and 100 nanometers. To put this in perspective, a nanometer is 1/1000th of a meter. A human hair is about 80,000 to 100,000 nanometers wide. At the nanoscale, materials exhibit unique properties that differ dramatically from their bulk counterparts. This includes enhanced catalytic activity, increased surface area, and quantum mechanical effects. You might ask, why does size matter so much at the nanoscale? The answer lies in the surface-to-volume ratio. As particles get smaller, a larger proportion of atoms are located at the surface. The surface-to-volume ratio is inversely proportional to the radius. This means that as particles shrink, their reactive surface area increases dramatically, making them exceptional catalysts. Now let's explore how nanocatalysts enable carbon dioxide conversion. Catalysts are substances that accelerate chemical reactions without being consumed. Nanocatalysts are particularly effective because of their high surface area and unique electronic properties. The key advantage of nanocatalysts is their enormous surface area. A single gram of nanoparticles can have a surface area exceeding 100 square meters, equivalent to half a tennis court. Here's how it works. Carbon dioxide molecules adsorb onto the nanoparticle surface. The catalyst provides active sites where chemical bonds can be broken and reformed, facilitating conversion into useful products. Let's examine our first major application, converting carbon dioxide into methanol. Methanol is an incredibly versatile chemical used as a fuel, solvent, and feedstock for producing plastics and other chemicals. The reaction is carbon dioxide plus 3 molecules of hydrogen gas in the presence of a catalyst produces methanol and water. Copper-zinc oxide nanoparticles, typically 5 to 20 nanometers in diameter, are highly effective catalysts for this reaction. The nanoscale structure creates an optimal balance of copper and zinc oxide phases. You might wonder, where does the hydrogen come from? This is a crucial question. Ideally, we want to produce hydrogen from renewable sources, like water electrolysis, powered by solar or wind energy. This integrated system uses solar energy to split water into hydrogen and oxygen. The hydrogen then reacts with captured carbon dioxide in a reactor containing nanocatalysts to produce methanol. The reaction typically occurs at 200 to 300 degrees Celsius and pressures of 50 to 100 atmospheres. These conditions are significantly milder than traditional processes, thanks to the enhanced catalytic activity of nanoparticles. Our second application is perhaps even more remarkable, directly converting carbon dioxide into polymers and plastics. This addresses two problems simultaneously: reducing CO2 emissions and decreasing our reliance on petroleum-based plastics. One exciting example is polycarbonates. These are high-performance engineering plastics used in everything from eyeglass lenses to bulletproof windows to compact discs. The reaction combines carbon dioxide with epoxide molecules in the presence of a nanocatalyst to form polycarbonate chains. Zinc-based nanocatalysts, often combined with organic ligands, facilitate this polymerization. The catalyst coordinates both the carbon dioxide and epoxide molecules, enabling them to react and form polymer chains. What makes this approach revolutionary? First, it uses carbon dioxide as a raw material, effectively sequestering it. Second, it reduces dependence on fossil fuels. Third, the resulting polymers can be biodegradable under certain conditions. You might ask, can we make other plastics from carbon dioxide? Absolutely. Researchers are developing nanocatalysts for producing polyurethanes, polyesters, and even polyethylene-like materials from CO2. Our third application addresses energy storage and transportation, converting carbon dioxide into synthetic fuels. This is particularly important for sectors that are difficult to electrify, like aviation and shipping. The Fischer-Tropsch process, enhanced with nanocatalysts, can convert carbon dioxide and hydrogen into liquid hydrocarbons ranging from gasoline to diesel fuel. The general reaction is, N molecules of carbon dioxide plus 3 N molecules of hydrogen produce hydrocarbons with N carbon atoms plus water. Iron or cobalt nanoparticles, supported on materials like alumina or carbon nanotubes, serve as catalysts. The support material stabilizes the nanoparticles and prevents them from aggregating. The nanoparticles provide active sites where carbon dioxide is reduced and carbon-carbon bonds form. By controlling particle size, composition, and reaction conditions, we can tune the product distribution toward desired fuels. This creates a carbon-neutral fuel cycle. Carbon dioxide captured from the atmosphere or industrial sources is converted to fuel. When the fuel burns, it releases the same amount of CO2 that was originally captured, creating a closed loop. Let's explore two more products, formic acid and methane. Both have important applications and can be produced efficiently using nanocatalysts. Formic acid is produced by carbon dioxide plus hydrogen yields formic acid. This is a simpler reduction than methanol, requiring only 2 electrons. Formic acid is valuable for several reasons. It can be used directly in fuel cells for power generation. It serves as a hydrogen storage medium, releasing hydrogen when needed. It's also used in chemical synthesis and as a preservative. Palladium or ruthenium nanoparticles, often alloyed with other metals, are excellent catalysts for formic acid production. These noble metal catalysts can operate at room temperature and atmospheric pressure. Methane production follows the Sabatier reaction. Carbon dioxide plus 4 molecules of hydrogen produces methane and water. This methanation process creates synthetic natural gas that is chemically identical to fossil natural gas. It can be injected into existing natural gas pipelines and used for heating, electricity generation, or transportation. Nickel-based nanocatalysts are particularly cost-effective for methanation. When structured at the nanoscale, nickel exhibits high activity and selectivity, approaching the performance of more expensive noble metal catalysts. Now let's discuss a crucial aspect, how nanostructure design influences catalytic performance. The arrangement of atoms at the nanoscale dramatically affects reactivity. Factor 1 is particle size. Smaller particles have more surface atoms, but they can also be less stable. There's often an optimal size range, typically 2 to 10 nanometers, that balances activity and stability. Factor 2 is shape and crystal facets. Different crystal faces have different atomic arrangements and thus different catalytic properties. Nanocubes, nanorods, and nanospheres can exhibit vastly different activities for the same reaction. For example, palladium nanocubes expose predominantly 100 facets, which are particularly active for CO2 reduction. In contrast, palladium octahedra expose 111 facets, which may favor different products. Factor 3 is composition and doping. Introducing small amounts of a second or third metal can dramatically enhance performance. These dopant atoms can modify electronic structure, create new active sites, or prevent catalyst poisoning. Factor 4 is metal support interactions. The support material isn't just a passive scaffold. It can donate or accept electrons, stabilize specific nanoparticle geometries, or even participate in the catalytic mechanism. Let's explore an alternative approach, electrochemical carbon dioxide reduction. Instead of using hydrogen gas, we can drive the reduction electrically using renewable electricity. The advantage here is direct use of renewable electricity from solar or wind. We can perform the reduction at ambient temperature and pressure, and we have excellent control over the reaction by adjusting the applied voltage. In an electrochemical cell, the cathode, coated with nanocatalysts, reduces carbon dioxide. The anode oxidizes water to produce oxygen. Electrons flow through an external circuit powered by renewable energy. Copper nanostructures are particularly versatile electrocatalysts. Depending on their nanoscale structure, they can produce carbon monoxide, formic acid, methane, ethylene, or even ethanol from carbon dioxide. For carbon monoxide plus 2 protons plus 2 electrons yields carbon monoxide and water. For methane, carbon dioxide plus 8 protons plus 8 electrons yields methane in water. The challenge is selectivity control. With so many possible products, how do we ensure we get the desired one? This is where precise nanostructure engineering becomes critical. Now let's address the elephant in the room. If this technology is so promising, why aren't we using it everywhere? There are several significant challenges to overcome. Challenge 1 is catalyst stability and lifetime. Nanocatalysts can aggregate, oxidize, or become poisoned by impurities over time. Industrial processes require catalysts that last months or years, not hours or days. Challenge 2 is energy efficiency. Many CO2 conversion reactions are thermodynamically unfavorable, meaning they require significant energy input. We need to maximize efficiency to make the process economically viable. Challenge 3 is scalability and cost. Producing kilogram quantities of precisely controlled nanoparticles is expensive. We need to develop scalable synthesis methods that maintain quality while reducing costs. Challenge 4 is carbon dioxide capture and purification. Before we can convert CO2, we need to capture it from dilute sources like air or flue gas. This capture step adds cost and complexity. The complete system requires integrating carbon dioxide capture, purification, and conversion. Each step must be optimized for the overall process to be practical and economically competitive. Despite these challenges, research is advancing rapidly on multiple fronts. Let me highlight some of the most exciting developments. Single-atom catalysts represent the ultimate in miniaturization. Individual metal atoms, stabilized on a support, can exhibit extraordinary activity and selectivity. These catalysts maximize atom efficiency, using every single metal atom. Bimetallic and multimetallic nanoparticles combine 2 or more metals in precise ratios and arrangements. The synergistic effects can produce performance far exceeding single metal catalysts. Core shell nanostructures have one metal at the core and another as the shell. This architecture allows us to use expensive metals like platinum or palladium only at the surface, reducing cost while maintaining performance. For example, a gold core with a palladium shell. The gold core provides structural stability, while the thin palladium shell provides catalytic activity. Machine learning is revolutionizing catalyst design. Artificial intelligence algorithms can predict which nanostructures will be most active, screening millions of potential catalysts computationally before synthesizing the most promising candidates. Advanced characterization techniques allow us to watch catalysts in action at the atomic scale. We can observe how nanoparticles change shape, how atoms move, and how reaction intermediates form in real time. Let's discuss the potential economic and environmental impact. How significant could this technology be? Global carbon dioxide emissions are approximately 40 billion tons per year. Even converting a small fraction would have enormous impact. The market for products like fuels, plastics, and chemicals represents multi-trillion-dollar industries. Carbon dioxide-derived products could capture significant market share while reducing emissions. Consider this example. If just 1% of global plastics came from carbon dioxide, that would convert approximately 3 million tons of CO2 annually while displacing petroleum-based production. This technology would create jobs in green chemistry, advanced manufacturing, and renewable energy sectors. It represents an opportunity for economic growth aligned with environmental goals. You might wonder, how close are we to commercial implementation? Several pilot plants are already operating. Companies in Europe, North America, and Asia are scaling up production. Full commercial facilities are expected within 5 to 10 years for the most mature technologies like methanol and carbon monoxide production. More complex products like drop-in fuels may take 10 to 15 years. Looking forward, the future of nanochemistry-enabled carbon dioxide conversion is bright, but success requires integration with other technologies. First, integration with renewable energy systems. Carbon dioxide conversion facilities should be coupled with solar, wind, or other renewable sources to ensure the entire process is carbon negative or carbon neutral. Second, developing carbon capture and utilization infrastructure. We need pipelines, storage facilities, and centralized conversion plants or distributed systems at emission sources. The integrated system connects renewable energy production, carbon dioxide capture, catalytic conversion, and product distribution into a cohesive circular economy. Third, policy and economic incentives. Carbon pricing, tax credits for carbon dioxide utilization, and mandates for low-carbon products can accelerate adoption. Let me conclude by summarizing the key points from this lecture. First, nanocatalysts, with their high surface area and unique properties, enable efficient conversion of carbon dioxide into valuable products that would be impractical with conventional catalysts. Second, multiple pathways exist for converting CO2 into methanol, plastics, synthetic fuels, formic acid, and numerous other chemicals. Each pathway has specific nanocatalyst requirements. Third, precise control of nanostructure, including size, shape, composition, and support interactions, is critical for achieving high activity, selectivity, and stability. Fourth, significant challenges remain in catalyst stability, energy efficiency, scalability, and cost. However, research progress is rapid, and commercial implementation is approaching. Fifth, integration with renewable energy and carbon capture infrastructure is essential for this technology to achieve its full environmental and economic potential. Here's a final thought to consider. Nanochemistry-enabled carbon dioxide conversion represents more than just a technological solution to climate change. It embodies a fundamental shift in how we think about waste. Carbon dioxide, long viewed as a waste product and pollutant, becomes a valuable feedstock. This paradigm shift from linear, take, make, dispose to circular use, reuse, convert is essential for a sustainable future. The promise of this technology is twofold: mitigating climate change while creating economic opportunities. It shows that environmental sustainability and economic prosperity need not be in conflict. Thank you for your attention. I hope this lecture has given you insight into the exciting field of nanochemistry and its applications in carbon dioxide conversion. This is a rapidly evolving area with tremendous potential to shape our sustainable future.